My name is Pranav Nidderworth, and this is my Lab 3 Circuits video. The purpose of this lab was to use the principles of energy conservation to predict circuit behavior, and to use an online model to validate those predictions, and to use multimeters to measure circuit voltage and current. So there's a few assumptions we made in this lab. The first, that there's no internal resistance in the battery, and that there's negligible resistance in wires. And we also assume that there's no significant loss of energy outside the system, so the energy is always conserved. The system is the circuit, and the surroundings is everything else. But because we're assuming there's no loss of energy, there's no interaction between the two. So there's a few principles we're using. The first are Kirchhoff's Lewd and Nope rules, which essentially state energy conservation, voltage conservation, and current conservation. Ohm's law, which is V equals IR and relates voltage to current and resistance. And capacitance, which is charge per voltage. Our results were that the current in the wires was predicted as 0.02 amps, and our model confirmed this, and voltmeters have high resistance and ammeters have low resistance. We were also able to show that in RC circuits, current is a function of time. So in the beginning of this experiment in part 1, we had two batteries, each of which were 1.5 volts, and two resistors, which were 47 ohms and 100 ohms respectively. And we had two ammeters placed to measure the current in both locations. Due to the node rule, there's only one node in the circuit, so we knew that I1 and I2 were equal. And so we were able to use Ohm's law to calculate the current in both of these positions. So since they're in series, we were able to add the resistances of each resistor to 147 ohms, and we know the total voltage is 3, and so we were able to find or predict that the current would be 0.0204 amps. And when we plugged this into the model, we found that this was 0.02 amps. I also reversed the ammeter, and the current was the same, including the sign of the current. So in part B, what we did is we took a voltmeter and replaced the ammeter, and we connected the voltmeter in series. And so what this showed is that the current throughout the circuit is 0 since it's an open circuit, and the voltage across the cap was 3 volts. So what this means is that an ideal voltmeter has infinite resistance, which is what's causing the current to not flow throughout the circuit. I then measured the change in voltage across each section using a voltmeter. Across the batteries, there's a +3 voltage difference. Across all the wires and ammeters, there was a 0 voltage difference. And across the resistors, the 47 ohm had a negative 0.96 volt difference, and the 100 ohm had a negative 0.024 volt difference. And so when you add up all the voltage differences, it comes out to 0V, which is obeys Kirchhoff's loop rule, as there's only one loop. A couple of observations we made. When we attach the voltmeter, we're attaching it in parallel, and it did not change the current, which leads me to believe that there's infinite resistance in an ideal voltmeter, as it was drawing no current out of the system. However, when we attach an ammeter in parallel, there was a change in current. I think this is due to the fact that the ammeter has 0 resistance, and thus the current will travel through the ammeter rather than the resistor that is attached in parallel to. And over here we have the graph of our. So we were able to calculate the resistance using Ohm's law in each of these sections. So the 47 ohm resistor was calculated to have 48 ohms of resistance. The 100 ohm resistor was calculated to have 102 ohms, and the wire and ammeter were calculated to have 0 ohms. So this deviation was likely due to rounding error, as the ammeter in the circuit only displayed 3 digits, whereas when we calculated it, obviously it's 0.0204. So I was willing to conclude that the model matched our prediction. In part 2 of the experiment, we used an RC circuit, which contained a capacitor and a bulb. And so we noticed that the current changes over time as the bulb grows dimmer, and the capacitor discharges when the battery is removed and it's attached to the bulb. When we doubled the resistance of the bulb, we also doubled the time it took to charge and discharge the capacitor. So in this experiment, we then took a 9-volt battery, a 0.2 farad capacitor, and a 30 ohm bulb, and we plotted the natural log of voltage over 20 seconds as it discharged. And using this, we were able to find the RC, which was found to be 1 over the slope. And so from this experiment, we were able to create a standard curve, and according to the standard curve, the slope was negative 0.1667, and negative 1 over that was equal to 6.024 ohm farads as our experimental RC value. And theoretically, R times C would be 30 ohms times 0.2 farads, and that would be 6 ohm farads. So we got a pretty close value between our experimental and theoretical methods. Given that this was an ideal simulation, the only source of error was human, so just clicking the stopwatch button to time the discharge amount. If we were to do this experiment in real life using an actual ammeter, we would have some resistance from the actual ammeter, whereas the ideal one would have none. This would cause the measured current to be lower than what it is actually due to the extra added resistance. If you were to do the discharge experiment in real life, we would, with no resistor, our model would predict the charging time to be faster than it actually would be due to internal resistance in the battery and high resistance through the wires. Due to this, the capacitor would take longer to charge. But overall, this model was successful, and we were able to validate predictions and details of multimeters.